we talk about the closed loop system Paul problem. Now let us discuss the state estimator. Now, can this Paul placement technique be used for state estimator? And the answer is yes. So we're going to tell you how to do it. Now, there's a called Debbie observer gain for the same case, delta t equal to 1, and the and g equal to 0, 1. Then we have a bar plus a plus gc. Then we have a bar square equal to 0, 0, 0, 0. So we have a state estimator problem here. And the observer equations, we know that is equal to x hat. Again, this is the hat. Talk about it, x hat. Sorry that this Microsoft is really, I hate this Microsoft since. All right, this really the head. All right, and this is the head, and this is the head. All right, and this is y hat equal to cx hat, cx hat plus duk. And that is the state observer you learned already. And so that observer here, x hat and w dot hat, and we have w dot wk hat, w dot k, and then y hat and yk hat, and so on. That's the state estimator. But this is Debbie. As a matter of fact, the same technique we can also do for the call state estimator. And for this case, now we just move all the state estimator Paul to the 0. So this Debbie means we move all the Paul to the 0. And that can be done too. And in your homework, then that's one way to do it, is just use the a bar square equal to 0, 0, 0. That's one way to do it. Another way to do it is you can do exactly the same what I show here, except now my Paul is 0, 0, and my Paul is the closed loop observer Paul will be 0. So we have here we have open loop. We have open loop. Again, we have open loop observer. That means we don't have the g equal to 0, and we have a closed loop. That's not called closed loop. We call observer. Okay, observer Paul. Pause. And open loop pause. Alright, so my open loop pause for this case is lambda equal to plus minus I, and that's in the unit circle is exactly the same as what you got there is I and I. So this plus I, this minus I. And for observer Paul, that's a bar, the eigenvalues of a bar. Now that's a bar. So the a bar equal to a plus gc. All right. And for this case, a is 0, 1, minus 1, 0, plus g is g1, g2, and c is equal to 1, 0. All right. Then our cross loop will become z1, 1, and minus 1 plus g2, 0, and that's my observer. This is my observer matrix. That's my observer matrix. Now, if my observer matrix, if this eigenvalue the eigenvalue, the desired eigenvalue, desired eigenvalue are 0. This is my desired eigenvalue called that's desired eigenvalue that's equal to 0. Then all eigenvalue equal to 0. And this one we call the that B. This we call that B. B. Okay. So if you solve this, the eigenvalue problem of this design, the manifest eigenvalue of that equal to, now the eigenvalue of A bar then that equal to, that means we need to solve Z1 minus lambda 1 and minus 1 plus Z2. Then we have a minus lambda that equal to 0. If we solve this problem, then and then if we solve this and that lambda equal to 0, then we'll find out that the G1 and G2 will be G1. If we solve this, then you will find out that the G1 is equal to, just like there, 0, and G2 equal to 1. If you don't believe me, then you can G1 equal to 0, and G2 equal to 1, 0, 0. Then that's lambda equal to 0, 0. Right? If this 0 and this 1 and this 0, this means 0, that means this minus lambda 1, 0. Eigenvalue of that will be 0, 0. Agree? So there's two ways to do it. You either solve this A bar, you can solve this, or solve A bar square equal to 0, 0. And that equivalent to solve this eigenvalue problem and set the desired eigenvalue equal to 0. So the same placement technique applied to the observer problem means we move the open loop pulse to the observer pulse, and that observer pulse is all 0, 0. That's the step B. So this is observer pulse is all 0, 0. So move from here to there, move from here also to there, and if I do that, then that means this is step B, observer. We call step B observer. Step B observer means observer eigenvalues are all 0, 0. So in your homework, as a matter of fact, you can do this way too, if you like, rather than go to solve the A bar square 0, 0, 0, 0. That's one way to do it. That's another way to do it, and they represent the same thing. Okay. Now, if you don't believe me, that is put in here, this one in there. That means I have lambda 1, 0 minus lambda that equal to 0. That implies what, lambda square equal to 0, right? So that implies lambda equal to 0. So that's the solution. I just use that way. Okay. Now, if we that's for this estimator, that means we have Okay, let me show you what I got here. All right. Sorry about this. And this is head. This head. This head. This head. And that's head. Just don't use office. If you use office, you have a different computer platform, then you get this problem. If you don't use that in your office, then you won't have a problem like this. And so, because my feedback, I have only W measurement. Here I have W measurement. See? I have only displacement measurement, but my feedback, my feedback, I need the one we designed earlier. We need the W dot head, but we don't have W dot the measurement. So the only way we can do is we go through the computer will go through this computation to estimate our W and W dot for us to feedback. Understand now? If we have a W, the only measurement we have is Y equal to W. That's the only measurement. But our control law, if you remember about three slides earlier, then the state feedback require W and W dot. Did you remember that? Right? So we have a 1/4. We have this because we need this guy. We need this guy. We have that guy. We have W, but we don't have W dot. And this state estimator gives us W dot, the estimate one. It's not true W dot, but it's an estimated W dot. However, in theory,